Namaskara. In this session we will continue our discussions on Prim's algorithm, the continuation of this. So, what we have seen so far is for every vertex, let us say x, y, z, maintaining the partner of x, the partner of y and partner of z, helps in reducing the cost of finding the minimum weight crossing edge if we maintain for each x in S a px in V minus S such that x px is a minimum weight crossing edge from x. If we maintain for each x a px satisfying this condition, then a minimum weight crossing edge from S to V minus S can be computed in time cardinality of S, because find out the minimum of these edges and that will be the minimum weight crossing edge from S to, this is S, this is V minus. But therefore, always cardinality of S is less than or equal to n. Therefore, I am able to find the minimum weight crossing edge very cheaply, but I need this information. How do we maintain this information? When you update the cut, this information will also change. Okay? Specifically, here is the worst case change that is going to happen. Suppose you have x1, x2, xk, and for all of them there is some y who is a partner. The minimum weight partner for x2 is also for everybody y is, suppose y is the minimum weight partner. Suppose px1 equal to y, px2 partner of x2 is also y, and pxk is also y. Suppose x1y is the minimum weight crossing edge. Then as our plan, we are moving y to S. This is S, this is V minus. We move y to S, because x1s, x1y is the minimum weight crossing edge. Then it is going to be like this, x1 now who is the minimum weight partner of x1? x1's minimum weight partner has come over here, and x2's minimum weight, who is that? And even for y, who is the minimum weight partner? How do we find this? You have to scan their adjacency list and figure out who is the minimum, because it has lost the minimum, and among the remaining neighbors we have no idea who will be the minimum. So you have to scan, that means updating may cost order m. That is because the degree sum is order m. Sum of the degrees of the vertices is order m. So, other than this, all other edges you have to consider, and that is proportional to the degree sum. Degree sum is proportional to m. Therefore, while finding the minimum weight crossing edge has come down from m to n, that requires an information whose updating requires order m. So, we are not seeing any benefit here. Anyway, that step is taking order m, right. Therefore, we are running into a kind of a problem, right. We are not able to get any benefit because if we have some information, I can use it efficiently to find the minimum weight crossing edge. But maintaining and managing that information is order m, and therefore, in every iteration I end up spending order m time. Again we have an NM algorithm. Therefore, this idea is not leading to any improvement. However, what Prim has done is a very clever observation. Okay? It is a very subtle and clever observation. This is usually done by mathematicians in mathematics. For example, if there is a double sum, changing the order of summing may lead to something easier to evaluate. If the same thing can be done in two different ways, one way may be very difficult, but other way may be easy. It's the same thing, but you are doing in two different ways. It's done usually in combinatorics. While counting, you get identities. One identity is easy to simplify, another identity will be very complicated, another part of the identity will be fairly complex, but both of them are same. That's the power of identities. It provides another way to evaluate certain things. So, if one way of doing is difficult, find out an equivalent way which is probably easier. Okay. In integration, for instance, we know theoretically that integral a to b and integral c to d of f of x y dx dy is same as changing the order. It does not matter, it is the same. But after changing the order, it may become very easy to evaluate, whereas the original one may be very complex. So, all these things we have seen in mathematics and in various situations where if one way of doing is hard, and if there is an equivalent way we can find, and if that is easy, we can get the job done by taking the other way. That is what we are going to do here. This insightful move is what made Prim's algorithm a classic one. What Prim has done is the following. He is maintaining the information of minimum weight crossing edge for each vertex in V minus S rather than from S. That does not matter as far as finding the minimum. So, you want to find out the minimum weight crossing edge. So, for each x in V minus S, maintain its partner in S, this is V minus. For each x belong to V minus S, let Px belong to S, this y is Px actually. for each x belong to V minus S, Px belong to S such that x Px is a minimum weight crossing edge from X. Maintain this information. Okay. The reason is the elements of the sets are not moved out. So there is no question of X losing its partner. In the previous case, X may lose its partner. In fact, several people may lose its partner, and for every one of them you may have to find. But here all elements of S are there as it is. That gives an interesting advantage. Okay? So for each x belong to X, V minus S. So again, how do you find the minimum weight crossing edge? Consider all edges of the form x Px where x belong to V minus S and find a minimum weight crossing edge. This can be done in cardinality of V minus S time, because only that many edges you have to consider for each element. If this is y, you have partner of y. Whatever is the number of elements in V minus S, each maintains one partner, the minimum going out from that overall. So the crossing edge is now viewed from V minus S. The set of all crossing edges can be viewed from S, or the set of all crossing edges can be viewed from V minus S. This is the view we have taken from V minus S. So we have taken a view of crossing edges from V minus S. We view all crossing edges going from V minus S. It is an undirected graph. You can view them as going from S, and from for each vertex in S you can maintain the minimum, or you can view it from V minus S to S. The earlier view is from S to V minus S. Now we view crossing edges going from V minus S to S. This gives a tremendous advantage in updating P of a vertex. In updating P of a vertex, this gives a tremendous advantage. Okay. How do we get the advantage in for updating? What advantage this offers? Okay. If we have all these edges, vertex to the minimum weightage, the partner, find the minimum only among them. That gives you overall minimum weight crossing edge. Now, how we can do the updating efficiently, or what is the cost of updating? So let us look at the picture. We have for Z P of Z. Let us say for V there is P of V, okay. Let us also assume that VPV is the minimum weight crossing edge. VPV is the minimum weight crossing edge. Let us assume that VPV is minimum weight crossing edge. Then we are going to move V to S. We are going to move V to S. So what happens is I have X, I have Z, X has got P of X, Z has got P of Z, and V P of V. V is moved here. Now let us consider X. S is changed. The definition of minimum weight partner is from X there are a lot of crossing edges going into S and you have to find a minimum weight crossing edge. Current minimum is P of X, but S is updated with V. S is updated with V. So S has changed. Will the minimum weight partner, will P of X change? Because V is added, will P of X change? Well, consider the following situation. I have let us assume that X is adjacent to V and X is not adjacent to Z. Okay, let us not even draw the dotted line. Let us assume that X is adjacent to V but Z is not adjacent to V. When you move V to S, this is S, this is V minus S, this is S. You see that Vx is an edge, earlier Vx was an internal edge, now Vx is a crossing edge. A new crossing edge is created. Moving of V, let X belong to adjacency of V. Moving of V to S creates a new crossing edge from X. This is the new crossing edge that is created. Earlier V was not there, now V is there and this creates a new crossing edge. Therefore, the minimum may have to be updated for X. We may have to check whether this is creating a smaller weighted crossing edge. If so, the partner of X will change to V, otherwise the same partner will continue. P of X will not be changed. P of X will be updated to V. P of X is some vertex now, but that will be updated to V if the new crossing edge created because of the movement of V has less weight. In other words, if weight of xv is less than weight of xpx. xv is the new crossing edge created, that happens to have a less, and then parent of x equal to v, not parent, sorry, partner of x is v. The partner is, that's all is to be done for updating. The partner information is not altered for vertices like z. Look at this picture. V and z are not connected, they are not neighbors. You have moved v, but that is not changing the crossing edges from z. The same set of crossing edges as before. It is not creating any new crossing edge from z. Movement of v is not altering the crossing set edge from z. Therefore, the current minimum remains the same. P of z is not altered, but for x maybe we have to change. So, the partner information is to be checked only for the neighbors of v which you have moved. The partner information is to be checked and updated only for the neighbors of v which you have moved. And updating can be done in order one time, because updating is this simple step. Therefore, updating can be done in time proportional to the degree of v, where v is the vertex that is moved. So simple. Earlier, partner information updating required order m time. Now, updating the partner information requires only degree of v, where v is the vertex that is moved, and this is a significant improvement. Okay, this is a significant improvement. So, we can now write the pseudocode. So, how do we plan? Initially, A is empty, S is some vertex r, S is some vertex r, and V minus S is V minus r in SR equal to 1, in SV equal to 0 if V is not equal to R. Okay? And now you have to update, you have to initiate the information on P of V for V belonging to V minus S. So, here is the S. S has got only one element R. So, R has got several neighbors, and V minus S has got some other vertices also, non-neighbors of R also it has. Okay. So, if this is X, this is the only neighbor, this is the only vertex, therefore, that is the minimum partner for X. For X, X does not have too many neighbors in S, X has got only one neighbor in S, therefore, that defines the minimum. So, for each V belonging to adjacency of R, P of V equal to R. For each V that is not in adjacency of R, that is not in adjacency of R, P of V is not defined. You do not define, there is no parent, there is no, sorry, there is no partner, there is nobody, there is no crossing edge at all. So, just do not define anything. But if X is a neighbor of R, then R is the minimum weight partner for X. Therefore, this is the way you have initialized. Now, for I going from 1 to n minus 1, what is that you have to keep doing it, right. 1, find minimum weight crossing edge, find a minimum weight crossing edge by considering edges of the form x px, where x belongs to V minus S. Find minimum weight crossing edge by considering edges of the form x px, where x belongs to V minus S. Okay. Let V PV be a minimum weight crossing edge. Considering edges of this form, find the minimum weight crossing edge. Let V PV be a minimum weight crossing edge. Move V to S. This is very simple. What do you do? In SV equal to 1, that is all. In SV will be 0 because it was in V minus S. Simply set that as 1. This is doing the job of moving V to S. Now you have to update, right. What is the third step? Update Px values for x belong to V minus S. For each x belong to V minus S, we may have to update the PV. So, how do you do the updating? It is simple. You do not have to touch all vertices. You have to consider only the neighbors of V which you have moved. So, for each x belonging to adjacency of V, right, only this you have to touch. For each x and x in V minus S, for each x in adjacency V and x in V minus S. How do you know x in V minus S? In S, x will be 0. That is what we mean by x in V minus S. If weight of xv is less than weight of x px, if weight of this edge is less than, then px partner is now V. The partner is now V. And VPV is what? Let VPV be the minimum you can okay, here itself we can add VPV to A. Earlier A is empty, right? We have yeah, A is initially empty. Minimum weight crossing edge is to be added to A. So add VPV to A, move V to S, and we have to update. So what is the total cost for this? The total cost for this is going to be the following. You have to find the minimum weight crossing edge by considering V minus S entities. V minus S is initially n minus 1 because one vertex is in S, n minus 1 vertices are in V minus S. You move one vertex, then it becomes n minus 2, then it becomes n minus 3. So you have to, in every iteration, you will be finding the minimum, in the first iteration you will be finding the minimum of n minus 1 values, then you will find the minimum of n minus 2 values. Therefore, the cost, total cost of step 1 across all iteration is order n square, n minus 1 plus n minus 2 plus n minus 3, n times n minus 1 by 2, right. The total is m times n minus 1, which is order n. The total cost of step 2 across all n minus 1 iteration is n minus 1 because moving is reassigning one bit, therefore that is one's cost 1. The total cost here is n minus 1. Updating is for each x in adjacency of V. Therefore, across all the n minus 1 iteration, it is degree of V and degree sum of V. First you might have moved some vertex, the complexity is its degree, then another vertex, the updating cost is proportional to its degree, whatever the vertices you have moved. Anyway you are going to move all the vertices, so it is the degree sum of all vertices. Degree sum of all vertices is 2m, which is order m. Therefore, the total cost of this is order n square plus m. The complexity of this implementation is order n square plus m. This is the first cut solution and implementation detail of Prim's algorithm. We can see how the asymptotic complexity of Prim's algorithm can be improved if we use heap and then Fibonacci heap. We will discuss the details of the same in our next session. Thank you.